see what we got here. We got in our second part of the fundamental theorem, it tells us that this big F here, defined by the area under the F curve, the little f curve. We know that big F's derivative is f of x. It's part of our fundamental theorem. We also can deal with that in the chain rule form, which means that if we do the derivative and that upper limit is not x, it's some other function like we had a minute ago with that x cubed, okay, that the answer is the f evaluated at the upper limit, so f of g of x times g prime of x. And notice that all that is just an application of the chain rule, isn't it? And it looks exactly like what any composition has, the chain rule. If we know that f is defined as a composition, the derivative is the integrand evaluated at the upper limit times the derivative of the upper limit. So, question says check these results by performing 2 steps for each of the following functions in 1 through 3. So in our first one, we are dealing with here f being defined as the integral of f of t from 1 to x, and we want to find big F in terms of x. So step 2 here says take the derivative of the result to determine x. So there's 2 steps we're going to do for each of these. So the first part is that we want to find big F here, and so keep in mind that big F in our case is going to be just simply x cubed. Alright, why x cubed? Because if my integral is 1 to x of t cubed dt, then what is the derivative of this? And the derivative is the integrand evaluated at the upper limit. Fair enough? And keep in mind that the upper limit here is x, so there's no chain rule issue here, is there? Okay. So it's just simply x cubed. Alright, this one, 4x minus x cubed, and this one, cosine x. So, very simple to execute, because we just have an integral function, and the derivative is just the integrand evaluated at the upper limit. Okay. These all being integrands, the upper limit being x, so those would be our results. And step 2 says take the derivative, okay, of the result to determine f prime. Okay. So if we do the derivative, take our derivative of our result here, we're going to get 3x squared here, of course. It's going to be our derivative of big F. So we got 3x squared there. And then actually, I said that backwards. Oh, you know what? Never mind. I did that wrong. Let's try that again. They want us to do a little bit more than that. They want us to first evaluate this in terms of x. So let me show you what they meant by that. I read the thing wrong. So we know that that f of t, or big F, so we'll do this for number 1. So big F is equal to 1 over x of t cubed dt. Okay. All right. So here's what they wanted to do instead. We use the fundamental theorem. They're trying to get us to see why the fundamental theorem works. All right. So if we just did straight up integration here, if we did the integral, we'd have t to the 4th over 4 on 1 to x. True? And if we put an x in there, we're going to get x to the 4th over 4 minus 1 over 4. And that right there would be big F. Agreed? Okay. Alright, so that would be step 1. So this would be step 1. And I'll let you do it for the other 2 because the other 2 are exactly the same. So this is step 1, is actually doing the antiderivative of the argument, putting in the x and the 1, and getting this expression. So this is actually our function f. Okay? And then the step 2 is what's f prime? Well, in our case, what would f prime be here? What would be the derivative of this? It would be 4x cubed over 4, which would ultimately be what? X cubed, and the derivative of this is 0. And so what is, in fact, the derivative? X cubed. Now, going about it in that way, okay, again, anytime we do that, we could just go ahead and find the antiderivative, and we could plug in our numbers and get an expression for f. And then once we get that expression, we could take the derivative of that as such. Okay? But with the fundamental theorem, which way is easier? Just applying the fundamental theorem, or integrating first and then differentiating second? The fundamental theorem is much easier, isn't it? Okay. But ultimately, we're trying to get us to illustrate here, and like I said, I'll let you do the other 2, but they're just trying to illustrate the fact that that this works, that the fundamental theorem is going to work no matter what function that we have. Right? Which is good. All right. Let's look at our next page, because in this case we have a chain rule issue, so I want to do one of these here with you. And it says, let us consider the more difficult case where we have x squared as our upper limit. Okay, so this is where we have a chain rule issue. So check the results in 4 through 6. So we're going to do the exact same thing here. We're going to do it with a t cubed again. So we know that big F is equal to 1 over x squared, 1 to the x, or 1 to x squared of f of t dt. And in our case, that's t cubed dt. Okay. So step 1, this is what we're going to show in step 1. And again, you can mirror this same thing with 5 and 6. We're going to actually find the antiderivative, which is t cubed, or t to the 4th over 4 again, evaluated on 1 and x squared. And if we put an x squared in there, we're going to get x to the 8th over 4 minus 1 over 4. So that right there would be our expression this time for big F. True? All right. And then what we're going to do after that is we're going to find the derivative of big F. Derivative of big F would be 8x to the 7th over 4. So that would simply be 2x to the 7th. So that right there is the derivative of our big F function. All right. So if the fundamental theorem, if our work from the fundamental theorem is true, okay, we better get the same answer doing it the fundamental theorem way. Agreed? So let's check it out. If we have the 1 to x squared of t cubed dt, we know that the derivative of that is the integrand t cubed evaluated at the upper limit. So that would be, I'll do it over here on the side because we have a little more space. That would be t, or x squared cubed. True? We put the x squared in there, cube it, and then we'd multiply by the derivative of the upper limit, which is 2x. And ultimately, what is this? X squared cubed is x to the 6th, and x to the 6th times 2x is equal to what? 2x to the 7th. So either way, we got the same result. Shouldn't we always? Like I said. Okay, so these problems are just illustrating that the fundamental theorem, okay, works essentially, okay, for any function. Okay. All right. So on 7, 8, 9 here, we just have to apply the fundamental theorem with the chain rule. Okay. Number 10, let's take a look at number 10. We have the h function here, t cosine t dt from 0 to 2 pi. And our a here is to determine the critical numbers of big H. Okay, the critical numbers would be when h prime of x equals what? Equals 0. Okay, so when h prime equals 0, that would be the critical points, critical numbers. And so h prime here, though, remember h is defined as this integral. And we do have a lower limit, that's some a. And we have an x as our upper limit. So therefore, what is h prime? It's the integrand evaluated at the upper limit. So x cosine x. So our job is to figure out when is x cosine x equals, but x cosine x, when does that equal 0? Well, if we use the zero product property, we know one of the answers is 0 because of the x. Okay. When else does cosine equal 0 in order to make this sentence true? Pi over 2 and 3 pi over 2, cosine would equal 0. So those would be our critical numbers in that problem. Okay, we're just finding the derivative, set it equal to 0. B says determine which critical number corresponds to a relative maximum value of h. Okay. So again, this is the derivative. Okay. Keeping in mind here that 0 is an endpoint, and in the beginning of the problem, what did they do with 0? It's not included, is it? So really, should that even be in the list? So we really only have 2 in there. We have pi over 2, 3 pi over 2. So let's check it out. If we do our first derivative test, and again, 0 and 2 pi are endpoints, put those on there. We've got pi over 2, 3 pi over 2. All right. We know that in our derivative here, the x part's always positive because we're putting in numbers between 0 and 2 pi. So we need to ultimately determine when this is positive and negative. So between 0 and 2 pi, cosine goes from 1 down to 0, doesn't it? So therefore, this would be a positive part. We know the cosine is negative between pi over 2 and 3 pi over 2. That represents our second, third quadrants. And then this part represents the fourth quadrant, where we know the cosine is positive again. So again, which one has the relative maximum? Wouldn't it be pi over 2? So x equals pi over 2, we'd have relative max. And same reason, so relative min would be 3 pi over 2, because it goes from, the derivative goes from negative to positive. Alright, questions on that one? Alright, so like I said, if you didn't do these yet, just finish up these parts, and also numbers 5 and 6. Alright, and the rest of it, we have a little bit more for that one. Number 11 on the back page, we have a graph given, so I'll take a crack at that one. And then also worksheet 3 is the last part of that one. So we'll go ahead and stop.